My talk is actually going to be slightly different from what I intended to do, mostly because Barbara asked me to do a primer of isotope geochemistry so we could understand each other, or trying to. So please stay with me, wake up. It's early afternoon, and hopefully we can have a good discussion. Except that it doesn't work. Okay, boom. So, quick review of mantle geochemistry. Why do I think Hawaii is different from the others? And then an update of new recent data, basically indicating, you'll get it, that the deep mantle is more heterogeneous than what we thought initially. So, what we use, or what I use a lot, is isotopes. And I'm going to try to convince you that there are isotopes and isotopes. It's not all the same. And the major point I'd like to make is that we use these ratios. And why we use these ratios is because they are not changed between the source and the lava. So that's why we can analyze the lavas to have an idea of the source. Now, when I say that there are isotopes and isotopes, this is one example. So what we have here is abundance of isotopes, and we have time. The Earth formed here. And we have three different systems. The stable isotopes are useless for us trying to look at time evolution. They're very useful when you look at atmosphere and climate, but not for us. Then we have what we call the long-lived, they are long-lived isotope system, meaning that their half-life is longer than 100 million years. And that's the systems I'm going to use, the radiogenic system. And you can see, for instance, that the samarium-147 decaying in neodymium-143 has a half-life of 106 billion years. That means it takes 106 billion years for half the amount of samarium present initially to decay in neodymium-143. So that's very long. It also means we have to measure things precisely. Then there is another series of isotopes that are produced, but that are also very unstable. They have a very short half-life, less than 100 million years. And Maud will talk to you about this, an example, the 146 samarium to 142 neodymium. Now, the key here, so it has disappeared basically. There is no more 146 samarium. So you can't compare what's happening with 142 neodymium with 143 neodymium. Even if for you it looks it looks very similar, it's actually giving you very different messages. So let's focus on some of these. And I put this also because Maud, in a couple of talks, will talk to you about this. You can see that's an extremely long half-life, meaning the variation through time are even smaller, and it's very, very difficult to measure. So isotopes. So when we look at oceanic mantle lavas, and this slide is focusing mostly on oceanic islands. We have the morbs here, but you can see they're relatively contained. What we have, and the system here is strontium versus lead. So we have 87 rubidium decaying in strontium-87 and uranium-238 decaying in lead-206. It's a very long time integrated signature. This didn't happen yesterday. What we see is that we have a series of trends in this diagram. It's not a gunshot. You have trends that go towards end members. And there are not that many end members. The point I want to emphasize is that if we focus on the enriched mantle one, and I'll explain to you what we think the source of these are, we have Hawaiian Pitcairn, which are both in the Pacific Ocean, and then we have Kerguelen and Tristan and Goff that are on either side of the African LLSVP. We have Tristan and Goff here, and Kerguelen there, Hawaiian and Pitcairn. What I want to emphasize here is that obviously the combination of probabilities for this to be meaningful is very simple, but it could imply that the material that's creating the heterogeneity in the Pacific LLSVP is not the same than the one creating the heterogeneity under Africa. And the second point I'd like to make is that it's probably older under Africa. So what are these acronyms meaning? Here's a little translation. We have mostly, those are the most important. We have DMN, depleted morph mantle. So that's the source of the mid-oceanic rich basalts. It is depleted because the material has been extracted to form the continental crust. And I'm simplifying a little. Don't jump on me, please. Then we have enriched mantle 1, the one where Hawaii and Kerguelen are trending. It's a mantle that reflects addition of crustal material, potentially delaminated subcontinental lithosphere, recycled subducted ancient pelagic sediment. It's not everything. I mean, the signature is very specific. Enriched mantle 2 is the vertical trend. This has to be recycled oceanic crust because, and we don't all agree, so I'm giving you big picture. High mu is the horizontal trend in the strontium-lead diagram, where we have high uranium-lead, which leads to these very elevated lead isotopic ratios, the one that you observed in St. Helena and things like that. And then when we look at this diagram, and I'll get there, everything basically is converging towards one area here, which was originally called PREMA, for prevalent mantle. It's a very common component. It's also FOSO, and I know the geophysicists like to use this tetrahedron. It's a 3D vision with 3 isotopic systems. All the trends converge to this area. So it's called PREMA, FOSO, focal zone, and it has also been called C for common mantle. I will argue that this is the average Pacific deep mantle because we see traces of this component in Hawaii, in Galapagos, and in Rangelia, so basically at the extreme of the Pacific Ocean. The trends in these diagrams are mixing trends. And you can see they curved, and they curved because we're dealing with different chemical elements. So this is what I'm showing here. We have neodymium versus strontium, and the curvature of these mixing trends are function of the elemental ratio. So it's a concentration. They have nothing to do with the isotopic composition. The isotopic composition defines the position of the end member. So that's what this is. Now, if we see all these signatures in the deep mantle, isotopically, it's heterogeneous. And the interpretation that we all have is that that's related to the fact that we have subducting slabs and recycling, bringing material that has been at the surface all the way down to the core mantle boundary in some cases. Now, if we do some mass balance of recycled material, and we know that there is between 0.3 and 0.7 cubic kilometers per year of sediment that's subduct, it means that in 3 billion years, so basically 2/3 of the Earth's history, about 1/3 of the modern continents will have been recycled. This is not very much, but remember, some of these elements are very concentrated in the continents. So when you mix that with the mantle material, which is very low in this concentration, they dominate quickly the signature, the mass balance. The oceanic crust, 20 cubic kilometers per year subduct, which means that in 3 billion years, 5% of the mantle mass can have been recycled. So that's mass balance. And it's very clear that we were foolish to think many years ago that the mantle was going to be homogeneous. So we have seen this a few times, even if the perspective of the LLSVP is clearly evolving. Again, Hawaii, Pitcairn on the sides of the Pacific LLSVP, Kerguelen and Tristan on the extreme ends of the African LLSVP. I'll focus on Hawaii, and well, before that, you will know this publication by Zhao, where, and we should go back to the data of Norman Sleep. Actually, I would suggest that somebody should redo all these calculations with the plume flux. Hawaii is by far way, way more productive than any other mantle plumes. Today, it's about 100 times more productive than other mantle plume. And that's an important point. There are also differences in helium isotopic ratio. I'm not going to talk about that. So Hawaii, largest buoyancy flux, large erupted volume of lava. The interesting point, and that's where Hawaii is different from other plumes, is that it's becoming stronger with time. So that means we're not tapping the tail, or we're tapping more than one tail. It's becoming stronger with time, and I'll show you that. The other thing is that the volcanoes are arranged in two parallel geographical chains, which is quite funny, especially as they're only 50 kilometers away. They're dominated by tholeiitic composition, which is different from most of the other oceanic islands. And the interpretation is they have a deep mantle origin. Finally, the lower trend, so the southwest side, shows more enriched composition than the other side. A few diagrams to show you that. Distance from Kilauea, it's the equivalent of time. Today, about 45, 50 million years, and we go to 80 million years. You can see that you have a significant increase in volume flux, and it's actually raising very high when you come to the island, which also explains the fact that it's becoming larger. So the other thing is geographically, the volcanoes are distributed along two lines named from the biggest volcanoes. They also have different isotopic signature. So that's the same diagram than before, where I made the difference in between the Chaire Trent volcanoes and the lower Trent volcanoes. And you can see that the signature is completely different. The enriched signature is limited to the lower Trent. That has puzzled us for many years. In case you were not convinced that Hawaii is big, I like this cartoon. It's a rendering of the mountains from space. And when you do a cross-section and you take Hawaii from the bottom of the ocean, where it starts, it's over 10 kilometers tall, higher than Everest. There is also the Hawaiian swell, major bulge, that is about 1 kilometer high and 1,000 kilometers wide. It's the impact of the mantle plume that's bending the bottom of the ocean. So the data that I'm going to show focused on the chill stage, which is about 95 to 98% of the complete volume, the volume emitted on the island. I'm not going to talk about these other lavas. They're interesting for other studies or to answer other questions, but I will argue very strongly that they don't give you answers about the deep mantle source. And you can see that there is about 800,000 to I can't calculate, to whatever, 800,000 to 1.2 million years of activity of tholeiitic phase above the mantle plume. After that, the plate moves away. It looks very different on the field. Huge volume of lavas, while here you have individual little cones and volcanoes. So we look at two things, depending how much time we have. we look at the basalts on the archipelago itself, so everything that's above the surface, and we look at we go back in time to 45 million years. So there are isotopes, and there are samples and samples when you want to do accurate and precise isotopic analysis. I don't want to work with a powder that was made by somebody else. The risk that it might be contaminated is tricky. You're also not always sure where it's coming from, and so on. So we went and sampled most of the islands going from basically today to 5 million years. It's very different scenery, it's very, very different access to. We sample, we powder cleanly. Some of the samples have been dredged and drilled, and to eliminate completely secondary alteration, we need to do a very careful leaching. That's just dissolving secondary phases such as carbonates. We centrifuge, and then we separate the element we want to analyze on these columns and analyze them with various instruments. So I showed you strontium lead, two different elements. This is an important point. Here we are in lead. It's all lead isotopes. It's two long-lived decay systems, thorium-232 decaying in lead-208, uranium-238 decaying in lead-206. Long half-life. In a diagram like this, we have the same chemical elements. So when there is mixing, it's going to be between two end members, it will be a straight line. It's not a hyperbola. And when you have precision, an error that's good, like in this case with multi-collector ICP-MS, you basically end up with these trends, these lines. What does that mean? It basically means that the red data, for instance, in KR, can be a mixture of something here and something there, or even there. Lead shows you that the source of Y is quite heterogeneous. Now, these are small variations. Huh? We zoom in on a Y. It's still very a Y signature, but the improvement in the accuracy of your data and reproducibility of your data gives us a different perspective. Sometimes I'm concerned that we're looking too closely. It's like if you take a big magnifier and you won't see the big picture, but keep that in mind. So the original data published by Bouchami et al. In 2005, basically stemming from the Hawaiian drilling project, shows you these series of individual lines on the different Hawaii volcanoes, indicating a lot of heterogeneity. Now, it turns out that in a diagram like this, a line could be also, it could also represent an age information. But the age here for these two islands is older than the age of the Earth, and it doesn't work. I mean, those lavas erupted between yesterday and 1 million years ago, at least on the big island of 4 or 5 million years ago here. The ages here are more than 3 billion years ago. So it's a mixing line. Remember, when you have another isotopic system, these are basically the same lavas. You have a hyperbola, and it could appear that you only have two end members. Clearly, for lead, you have more. Now, that data is the same as on the previous slides. It's just that the authors colored them depending on which trend on the archipelagos they were coming from. We have LOA here, we have KR there, and basically the measure of the difference is this ratio, radiogenic lead, which represents the difference in this direction, and which is basically a proxy for thorium and uranium. And when you project that back in time, so that is today, we go there 5 million years, you can see that there is a nice dichotomy between the two. That paper, which really laid out the groundwork for all this, was mostly focused on the Big Island and a couple of other ones. So that's the samples that we resampled, only sheet lavas, and basically it confirms that for 95% of lavas in Hawaii, there is a difference between the lower trend volcanoes and the Chaire trend volcanoes. Yes, thank you. So if we focus on each volcano, so we have a line on each volcano. On the Chaire side, on the lower side, they rotated around an average composition for lower. On the Chaire side, they converge to a position there. So it's a different geometry which represents different characteristics of the source. So the way we interpret that, and that's a hypothesis, obviously, because as geochemists, we need you to be able to image this, is that the enriched character on the lower side, it's because it's tapping material on the southwest part of the trends, it's tapping materials, some materials coming from the Pacific LLSVP. It also explains a wider, you have more variation, it's more heterogeneous on the lower side than on the Chaire side. So more heterogeneous. Now, yeah, we need to cross boundaries, and I need to speed up. We went back. So we look at a few exceptions. Ko'olo, and then West Maui, East Molokai. You can see that there are differences. This data is lower. This data here is more, it's not going to the average lower. So what's happening there? Basically, that led us to do some statistical analysis, and we defined 6 groups that are independent on Hawaii. You can see here, just by plotting histogram of the 8:4 ratios, that indeed there is some overlap, but they spread. And then when you treat them with a parametric statistical analysis, we did PCA, we did LDA, it's all coherent. We have 6 different groups. And if we focused on Chaire and lower individually, we find their independent composition. There is a time constraint to that, there is a geographical coherency to that, in the sense that lower is always on the southwest side. The enriched part is only active for 1.5 to 2 million years. Here, Loihi hasn't been seen anywhere except very recently on this volcano, and Chaire is much less voluminous. So that's what we see here, where the size of the bubble is proportional to the volume of the volcano, and you can see that the lower side on the archipelago dominates in volume, which is reflected here by this histogram. So just to confirm the difference and the fact that the lower side is way more heterogeneous than the Chaire side. That led us to a revision of the diagram where you tapping different zones in the LLSVP to account for the differences on the lower side, and the Chaire side is sampling the average Pacific mantle. So, and obviously, this is the opposite of your coding, sorry about that. I wanted to keep the color that we use in our isotope diagrams, but you get a picture, and you can see that that explains the fact that these heterogeneities, and it's the models of Cynthia Farnetani, where they are finite in time, and which lower Lohihi, very... Now, I just spent all that time telling you that Loa was heterogeneous, so we decided to investigate another isotopic system. Nothing to do with time here. What thallium isotopes can trace is the presence of some iron manganese that could have been brought down in the subduction zone. And what we see here, so that's epsilon thallium. So contrary to all our expectation, the red is always the Chaire side. We have some higher ratio on the Chaire side, which reflects the presence of material oceanic crust associated material or recycled pelagic sediment. So what we see, and we observed also correlation between thallium isotopes and oxygen isotopes that confirm the fact that the chaos source is also heterogeneous. Again, we're not too surprised. And so I'm going to leave you with that, and I'll happily answer any questions. Thank you.